Hello everyone. In this presentation, I would like to introduce our study on the stress field evaluation in microstructured components with holes treated as Cosserat continua. I'm Farui. This presentation includes following sections. The first is the introduction or motivation of the study. Cracks or microstructures are widely exist in many materials such as this, which can play an important role in the mechanical behavior of this material. Cracks or microstructures normally distribute randomly with different lengths and directions, which can complicate the understanding of the material's response. So a non-local continuum is needed to describe the mechanical behavior of the microstructured material, instead of a classical continuum which cannot reveal the presence of the microstructures. A non-local continuum named the Cosserat continuum will be used here. The Cosserat continuum, also named the micropolo continuum. As we know, this continuum introduces an extra degree of freedom, which is the micro-rotation omega, and the kinematic equations and the stress-strain relations of this continuum are shown here, and their compact forms. We can see from the stress-strain relationships, the constitutive matrix has four sections coupling the classical measurements and the micropolo measurements. We should also note that in this continuum, the shear strain and the shear stresses are not symmetric. In the finite element method, as the introduction of the micro-rotation, the displacement field should include the micro-rotation field. Here we use different shape functions to interpolate the classical displacement field and the micro-rotation field. Shear and strain vectors are shown here, and according to the principle of the virtual work, we can have the element stiffness matrix and the element nodal force vector as here. Next is the numerical simulation. Firstly, we need to obtain constitutive matrix for Cosserat continuum by a homogenization process. Microstructured components can be considered as an assembly made of rigid rectangular blocks and the elastic interface as shown here, where the interface can represent the microstructures. 7 blocks RVE can be used for better simulation results. The different direction of microstructures can be represented by transforming the assembly angle beta from the lower xy coordinate system to the capital XY coordinate system. Here we select 6 angle beta as shown here, and for the different lengths or scales of the microstructures, that can be represented by changing the aspect ratio, rho, which is the ratio between the width and the height of the block. So here we select 4 rho. The corresponding RVEs are shown here. Here we show the constitutive components of the Cosserat model, and the Cauchy constitutive components are also obtained for comparison. We can see that there is no zero components when beta equals to 0 and 19 degrees. Actually, only diagonal components of the constitutive matrix exist, showing an orthotropic nature of the material. For other beta, all components of the matrix A and D appear, showing a central symmetric nature. Absolute value of these components may change homogeneously as rho increases. This is a result of the when rho equals to 7 and 15. We can see that when rho equals to 15, the values of the components are very high. The simulations will be performed on a classical tension problem of a square plant with a circle hole, as shown here, the sketch of this problem. This is the result of the horizontal displacement U2. For both two models, U2 has a direction effect as beta increases. It mainly increases and then decreases as beta from 0 degree to 115 degree. As rho increases, U2 has a reduction trend for both two models. The orthotropic material, that is when beta equals to 0 and 19 degrees, there is no obvious difference between the two models. Whereas for the central symmetric materials, when beta equals to other angles, the U2 from the Cosserat continuum is greater than that from the Cauchy continuum. That is the result of the horizontal stress sigma 11. We can see that the distribution of the sigma 11 show a very clear direction effect with respect to the beta. However, the direction effect is less evident for the shorter blocks when the rho equals to 1.5. As rho increases, sigma 11 is more evident and the high stress L become wider, except for the 19 degree. That is because the direction of the microstructure when beta equals to 19 degree is actually same as when beta equals to 0 degree, but the aspect ratio of the block are different. This is the result of the Cosserat relative rotation. The relative rotation is a peculiar element for the Cosserat model, and it also has a direction effect on its distribution, and this effect is more evident as rho increases. For the central symmetric material. For the orthotropic materials, relative rotation shows a nearly symmetric distribution where the positive and the negative values can be both observed. When beta equals to 13 and 17 degrees, the relative rotation is mainly dominated by the positive value. Oppositely, for beta equals to 120 degree and the 115 degree, it's mainly dominated by the negative value, indicating that the direction of the microstructure can not only affect the distribution of the relative rotation, but also affects its acting orientation, positive or negative. This is the result of the shear strain epsilon 1,2. Similar behavior can be observed for the epsilon 1,2 for the Cosserat continuum. Orthotropic material shows symmetrical distribution, and the direction of the microstructure affects the distribution of the epsilon 1,2 and its acting orientation. Epsilon 1,2 of the Cauchy continuum is also shows direction effect, but less than that of the Cosserat continuum. Epsilon 1,2 for the Cauchy continuum meaning less medial between the epsilon 1,2 and the epsilon 2,1 of the Cosserat continuum. This is the result of the epsilon 2,1 for the two models. Actually, As the shear strengths in the Cauchy continuum are symmetric, epsilon 12 and epsilon 21 are equal for this continuum. Epsilon 21 for the Cosserat continuum also show direction effects, but its distribution and acting rotation show an opposite behavior compared with the epsilon 12 of the Cosserat continuum. In this slide, the distribution of sigma 11 at the edge of the hole also has a direction effect, and it is more evident for high rho. The location and the magnitude of the pink stress also change with the beta for both two models. Such an effect is less evident in the Cauchy continuum than the Cosserat continuum, and such an effect also less evident for the shorter block. This slide shows the stress concentration factor SCF. The SCF is the ratio between the pink stress and the nominal stress. In general, SCF drops forcibly and then rises as beta increases. The smallest SCF normally occurs when beta equals to 19 degrees. The value is close to 3, whereas the highest SCF can be mainly found when the beta equals to 0 degree, around 4 to 9. For both two models, when rho equals to 1.5, the right line SCF shows the values most close to 3. That is the well-known analytic solution for an infinite isotropic plant with a circle hole. For high rho, the range of the SCF is more wide, indicating that SCF is more affected by the direction of the microstructure. The last section is the conclusions and some remarks. Firstly, we can conclude that a direction effect can be observed with respect to the transformation angle beta. The pink stress at the whole edge of the circle hole has different location and magnitudes for various beta. For the longer microstructure, the direction effect is more evident, and also for longer microstructures, the difference between the Cosserat and Cauchy results also become larger. The stress concentration factor SCF show a V-sharp from beta equals to 0 to 115 degrees. SCF is more close to 3 when rho is small. For high rho, it is more sensitive to the microstructure's direction. The Cosserat continuum can better describe the effect of the microstructures, as the introduction of the peculiar measurements such as the relative rotation and the unsymmetrical shear strength, because those measurements show a very different behavior among different transformation beta. That is all. Thank you for your attention.